Hello. We're about halfway through our chapter. This is all about polynomials. So polynomials we've talked about are linear equations, x to the first, quadratics, x squared, cubics, x to the third, quartics, x to the fourth, quintics, and so on. So today we're learning about what do we do if we don't know how to factor. So say you're given a function and let's give you f of x equals x cubed plus x plus 1. And I tell you to find all the zeros. You know you're going to have 3 zeros. You don't know what they are. Before, you would have just factored this. Well, you can't factor this. I mean, instinctually you can't. And then the chapter before, I gave you one of the factors, so then you were able to use division to factor to find the rest of the factors. But what happens if you're not given anything? You're just told to factor. Well, before we had graphing calculators where we could just put this into a graphing calculator and have it graphed and see where it would cross the x-axis or where it would be 0, René Descartes, a famous mathematician who came up with the x and y coordinate plane, also helped come up with the rational root theorem, or what textbook companies call now the rational zero test. And pretty much he noticed that there was a pattern between the leading coefficient and the constant. You notice there was a pattern between the two. If you took factors of the constant term and put them over factors of the leading term, you could get a possibility for all the zeros that this polynomial will have. So in this section, you're going to find all possible zeros of a function using the rational zero test. You're going to approximate the zeros. We're not going to actually do that. I'll explain the intermediate value theorem and find real zeros and sketch their graphs. So pretty much if there's a polynomial, the a's represent coefficients, x's are to whatever power you have, then every rational zero of f can come in this form. So here's the thing. This is only to find rational zeros, meaning fractions, whole numbers. But if one of your zeros is the square root of 7, you're not going to find it in the rational zero test because square root of 7 is an irrational number. And complex numbers, which we'll talk about in the next section, or imaginary numbers, you're not going to find here. So you can find up to 3. I don't know if we're going to, but we should be able to find at least 1. It says possible rational zeros are factors of the constant term put over factors of the leading coefficient, or P and Q. So we're going to call this P and this Q. Have no common factors other than 1. When the leading coefficient is 1, the possible rational zeros are simply the factors of the constant term. Well, duh, if it's over 1, that's it. So factors of 1 are 1 over factors of 1, which are 1 or negative 1 as well. Well, 1 over 1 is 1. 1 over negative 1 is negative 1. And those are the only combinations we have. So one of them should work. If I plug 1 in, 1 cubed is 1 plus 1, that's not going to work. If I substitute in negative 1 cubed is negative 1 plus negative 1, that's negative 2. Okay, there's no rational zeros. It's not going to work. It will have zeros that are either irrational or that are complex, which are imaginary. So let's try finding a different one. Let's use the example. We'll just go on example 2, and then I'll do another example in example 2. Well, example 2 in your textbook is f of x equals x to the 4th minus x cubed plus x squared minus 3x minus 6. Okay. I wouldn't know how to naturally factor that, so I'm going to use the rational zero test or the rational root theorem. Either one's fine. Like I said, it all depends on the textbook company. So you take factors of the constant and put it over factors of the leading coefficient. Well, 6, 3, and 2, and 1 are factors. So all the possible numbers you could get would be 6, -6, 3, -3, 2, -2, 1, and -1. All of these obviously won't work because you only have 4 zeros maximum, but one of these should work. One of these should work. Okay. So if I substitute in 6, will it work? It's kind of hard to substitute in. And what we just learned last section is using synthetic division. When you use synthetic division, not only are you figuring out if it is a solution, but you're also using division to keep breaking it down. So it's like killing 2 birds with 1 stone. So let's try 1 or -1. 1 or -1 are usually a good one to start with. They're very common. Let's try 1. Well, I can just do 1 in my head. 1 to the 4th is 1, -1, +1, -3, -6. Yeah, it's not going to be 0. Okay, let's try -1. I'm going to try another method of substitution, which is synthetic division. 1x to the 4th, -1x cubed, 1x squared, -3, -6. I could have just substituted it in, but I have a feeling it's going to work. Okay, just with the pluses and minuses. I'm going to bring 1 down. 1 times -1 is -1. -1 is -2. +2. 3. -3. -6. +6. 0. So that's your remainder. So yeah, it worked. If you have a remainder of 0, then it's a factor. And then it worked backwards. So how many solutions should I have? I should have at maximum 4. I don't know how many we'll have that are rational. So here we go again. X squared minus 2x squared plus 3x minus 6. Well, there's 4 terms here. I can go ahead and do this method again, taking 6 over, this should be a 3, over x cubed, 1x cubed. But I also see there's grouping here. Let's see maybe if I can create a GCF. Yeah, I can. Since I get x minus 2 twice. The GCF here was 3, I took it out. The GCF here was x squared, I took it out to create a GCF x minus 2. When I remove x minus 2, I'm left with x squared plus 3. So all our factors were x plus 1, because your solution is 1, and these 2. So we figured out our solutions are -1, +2, and if I set this equal to 0, and solve, I can't take the square root of 3. So I have 2 complex solutions, which we're going to talk about next section, and then I have 2 real solutions. So yeah, -1 worked and 2 worked. So this section just wants you to find the rational ones, the pretty ones, okay? Let's try another one. Let's use example 3 in your textbook. It says find the rational zeros of f of x equals 2x cubed plus 3x squared minus 8x plus 3. So it should have 3 zeros, whether they're real and rational, real and irrational, or complex meaning imaginary. Well, I can't factor like normal. I'm going to use the rational zero test. I'm going to take factors of 3 and put them over factors of 2. So you're going to have 3 and -3, 1 and -1 over factors of 2 and 1. So the possibilities are 3 halves, -3 halves, 1 half, -1 half, 3, -3, 1, -1. Like I said, 1 to go with is 1 and -1 usually to start. So let's just try 1. I'm going to use synthetic division because it's actually a lot easier than actually trying to substitute in. And if it does work, you have the new leftover polynomial. So drop the 2. 1 times 2 is 2. Drop the numbers 5. 5. Drop the numbers -3. -3, 0. It worked. So if 1's a solution and x minus 1 was a factor, what's left over? Remainder, constant, x squared. You're left with 2x squared plus 5x minus 3. Can we factor this? Well, I have 3 terms as x squared. Let's see. I'll need a 2x and an x because x times 2x is 2x squared. Factors of 3 are 3 and 1. I'm going to want to put 3 by the 2 so that when I multiply them together, I get 6. Because 3 times 1, you'll get 6 and a 1, which will give you a 5. You want a positive 6 and a negative 1. And this is just from practice. So if you're not good with factoring, this is going to be very hard for you. So now here's what I'm going to do is I'm going to introduce something else too. So look, all 3 answers are actually rational. We had a 1/2 in here, it worked, a negative 3 worked, and a 1 worked. So there happen to be all 3 numbers. So if you were to graph it, it would intersect at 1, 1/2, and negative 3. So probably it's going to look like this. I said Loch Ness Monster. We know we're going to, probably go something like this. Just to get an idea of in your head. Okay, same thing here. We're x to the 4th. Our zeros that are real are -1 and 2. So we probably have an arm up here and an arm up here. Who knows what's going on down here, but it's not crossing the x-axis. And then if we go back to the front, what did this thing look like? We didn't have any rational. Does it even cross at all? Well, it has to, because we know that x cubed kind of looks like this. So where did it cross at? And in your textbook, they show you it crosses between 0 and -1. So it's just not rational. It's just not a pretty number that it crosses that we can't figure out with this test. That's all. But it does have a 0. Okay, so that's all you're doing for this section. But let's go back to this. If you are unable to factor, this is called a quadratic. You're raised to the 2nd power. And let's refresh our memories. If you don't know how to factor and you have a quadratic, you can use what's called the quadratic formula. The quadratic formula is able to give you your x values by just using a formula. So instead of factoring, instead of completing the square, what you can do is just use this formula. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And where does it come from? It does actually come from completing the square. So somebody, I don't know who, here I'll show you real quick. Somebody realized that completing the square, if you just do it over and over, but just use letters, it's actually the quadratic formula. Let's see if I can find it. Well, let me write what it is. 2x squared plus 5x minus 3. So your A is 2, your B is 5, and your C is -3. When we solved this earlier, we got a 1/2 and a -3. So if we use this formula, we should be able to get 1/2 and -3. Like I said, you can use this if you don't know how to factor. So go ahead and put your B in. It's opposite of B, plus or minus b squared minus 4ac all over 2a. So it's -5 plus or minus the square root of 25 plus 24. That's a good sign already. Why is it a good sign? Because I see the square root of 49. And the square root of 49 is 7. So now we're going to branch off into 2 different possibilities. -5 plus 7 divided by 4 and -5 minus 7 divided by 4. This is going to become 2 over 4, which is a half. And this is going to become -12 over 4, which is actually -3. Math is beautiful. I know you probably don't think so, but the more you learn about it, it's just it's amazing. Okay, let's see if I can find this. I want you to see where it came from. There we go. Here's my super cool joke. Okay. So when you complete the square, when you have y equals ax plus b, or I'm sorry, ax squared plus b plus c, we always knew in the beginning we don't want that number in front. So we factor it out or we divide it out. So say that was like 2x squared. So you divide every term by that a or that 2 or whatever it is. Then we say to ourselves that c over a isn't any good, scooch it over. And then we say take our b, divide it in 2 and square it. And then we add it to both sides to keep it balanced. We divide it by 2 or multiplying by half. That's why there's a 2 down here. Now, if you're like, I can't follow it, that's okay. I'm just showing you where the quadratic formula comes from. Some of you are kind of be like, oh, that's kind of cool. If you go on the next page, it's the same thing. Then you're able to factor this. It's the same quantity twice. And then I brought that 2 in and the 2 in. And then I was able to get a common denominator and combine these. Same line. Then I took the square root of both sides. Then I moved that to the other side. So all I'm doing is isolating x. And then I took the square root at the bottom. And here we are. That's where you get the quadratic formula from, is just completing the square of a basic standard form or quadratic form equation, depending on the textbook you have. So that's where it comes from. All right, do the suggested homework problems, and we will go over them in class.